I think you should specifically be thankful that we saved this last section of Chapter 3 until after Exam 1, because otherwise Exam 1 would have, about half of Exam 1 would have been spent crunching numbers and doing stuff on the problems. So let's take care of it now. Couple of types of problems we'll do here. I try to make it clear here what information you're given and what you can calculate based on that information. So let's say you're given the elements present in a compound, like this, a compound made of CH and O. Okay? You're given the masses or mass percentages of those elements. Okay? Either one works fine. You can calculate the empirical formula. Now, do you remember what we said, how we said the empirical formula works compared to the molecular formula? What do you think?
The empirical formula is at its base, so like
yeah.
H2O2 would be
HO. Okay? It only shows you the simplest ratio of those elements, okay? Because that's what we can calculate just based on amounts of elements present. Now later on we'll talk about getting that into a molecular formula if necessary, but first we have to calculate empirical formulas. So here's our problem. Compound made of CHNO is found to contain these percentages of carbon, hydrogen, and oxygen. You probably won't always be told that, but these percentages are all by mass. Safe assumption to make if you're not told otherwise. We can calculate the empirical formula. Step 1, if given percentages, convert them to grams per 100 grams of sample. And that is the simplest conversion that you can possibly do. Because if I had a theoretical 100 gram sample, how many grams of carbon would that sample contain? Okay, let's not make that too hard. Grams, 5.0 grams, 26.2 grams of O. Now, I didn't have to give you that O there for that one. If you were given percents and you were given all of the percents except one element, you can just subtract them from 100, right? Because that's how percents work. If you were just giving if you're just given masses, okay, if I gave you masses of C and H, but I didn't give you the mass of O, what else would you need in order to get the mass of O? Yeah, if I gave you the total mass of the sample and masses of all but one, you could subtract from the total, okay, as long as all the elements were accounted for. Okay, so everybody okay on that? That's the easy part. That's not so bad. Okay, so now we got to set up some calculations. We've got these masses. We always have to start in grams each time. We're going to convert them to moles using the molar masses of those elements. So I want you to set up 3 calculations that look like this. 68.8 grams of carbon, 5.0 grams of H, 26.2 grams of O. Okay? And I want you to set up a conversion factor for each of those using the molar mass of those elements, just to convert them into moles. So give that a try. So make sure we can all do that first. Anybody need a calculator? Somebody got one? Fan out. Make sure the unit cancels, so grams has to be on the bottom. Yeah, there. Yeah. Yep. Set up a canceling unit, set up grams on the bottom and moles on the top, right? Okay. Do not round your answer, at least not to that number of sig figs. If you're going to write down an answer, give it at least 2 extra sig figs what you're writing down. Okay? Rounding errors are a really big deal in these kind of calculations because you have 4 or 5 steps in the calculation. And yeah, give at least 2 extra sig figs. Maybe underline the uncertain digit and write 2 or 3 more after that. Did you give 5 point something for the first one? Yeah. 856 or something. 72. Yep. I'll just do 86. Oh, and that's not grams, that's moles, right? Okay. So I underlined the third significant figure just so we can keep track, but I wrote down some extra digits so we don't have rounding errors. 4 point something for H? Yep. Let's underline the 9 there. Of H. Okay, 1 point something? Is that right? Yep, that's what I got. Okay, so far so good. All right, 3 sig figs. Alrighty. So, honestly, the first step for most calculations in chemistry involves converting it into moles. So that's always a safe assumption. If you're starting with grams, convert it into moles if it's any kind of amount-based calculation that happens. So we got grams of our 3 elements. We've converted them into moles. We did that successfully. So if you could please on your notes select, copy, and paste those values onto the next page. Well, you can't do that? Why not? Okay, I'm just going to put them right here, just so we can see them. Whoa, not that. That's kind of fun. Okay. Alrighty. Ultimately, what we're interested in here is a formula. Number. So, we're going to make what looks like a formula, right, out of C, H, and O. Okay. We're going to say C, H, and O. And to get the ratio of elements there, it's pretty much just reducing these numbers to something that's a ratio to 1. So all we have to do is look at these numbers. We find the smallest, okay, which is that one, and divide all 3 by the smallest value. So carbon, that's going to be 5.7286 over 1.6375. H is going to be 6375 over 6375, and we know what that is. Okay. Or no, that was O, sorry. Wrote the wrong one in here. That's that one. H is 4.9603. Okay. All right. So, let's put an approximately equal to. Okay. So what did you get for C? Maybe rounding it to just like 1 decimal place. Okay? Because usually those will be round-ish numbers. If they're not right on a number, they'll be on like a half or a third or a quarter or something like that. Okay? So let's call that, let's call that 3.5. What about H? If we're bringing that to kind of a roundish number or a roundish fraction of a number. Yeah, let's just call that 3. And that O is just going to be 1. Okay? So all that process did was simplify those 3 mole values to a ratio where we've got something to 1. Okay? Where our lowest value is represented as 1. Okay? Then all we have to do, if necessary, we will make all those subscripts into whole numbers by multiplying by the smallest value possible to make those round values into whole numbers. Okay? So what would I have to multiply all of those subscripts by to make them all whole numbers in this case? Yeah, if we double them all, if you got a 0.5, you double everything, that'll make it all whole numbers. Okay? So if we're multiplying by 2, C 3.5, H 3O, okay, times 2 for all those, that becomes C7, H6O2. That is our empirical formula. Okay? All those last 2 steps did was to get us the simplest whole number ratio of those elements. Okay? So that's just the way using algebra. If we've got raw mole values, okay, to convert those into a simple whole number ratio. We learned from the law of multiple proportions that compounds have whole number ratios of elements in them, right? So to get just raw mole values into whole number ratios, we reduce it all the way down so that the lowest is 1, and that's why we divided all of them by the smallest. And then if we're not at whole numbers, we double or we triple or we quadruple, something like that. Okay? Whatever the smallest integer is to multiply them by so that they become a whole number ratio. Okay? So that's an empirical formula. Let's actually just write here. So that'll be useful for us. That is the simplest whole number ratio. Okay? That does not tell us what one particular molecule, if it's a molecular compound like this, that doesn't tell us what one molecule looks like, okay? But it does tell us at its rawest form what the simplest whole number ratio of that would be. Okay? So